Okay, so the electromagnetic spectrum is just a name for the range of radiation. Let me tell you what they are. So that's the lyrics to the song that is posted in this thread. I don't know how useful it is, but it seems to help some people remember this stuff. It has 2.5 million views, so I guess it must be an excellent song. I'm sure you'll love it. So, we've been discussing electromagnetic radiation, where an oscillating electric field produces an oscillating magnetic field, which then induces an oscillating electric field. And this propagates as a wave. So, all of the different types of electromagnetic radiation are the same thing. They are all electromagnetic waves, however, they have different wavelengths and different frequencies, and this causes them to have different energies. Because they have different energies, they have different effects. This slide is showing the electromagnetic spectrum as a function of wavelength, with high energy to the right and low energy to the left. That means that low wavelengths and high frequencies are to the right, and the low frequencies and high wavelengths are to the left. One way of thinking about this is that if the frequency is large, then the electric field is oscillating back and forth very rapidly. So it must be carrying a lot of energy in order for the wave to do that. This slide is also showing the electromagnetic spectrum, but it's flipped here with the low energy to the right and high energy to the left. This one lists the wavelengths, so you can see how the different types of electromagnetic radiation change with wavelength. I guess we'll start with the middle here with visible light. So visible light is the portion of the electromagnetic spectrum that our eyes detect and can tell colors from. So it is 400 nanometers to 750 nanometers. 750 nanometers corresponds to red and is the low energy portion of what we can see, and 400 nanometers corresponds to violet, which is the high end of the energy range that we can see. If we go to higher energy and shorter wavelengths than violet light, we go to ultraviolet light. That is light that is higher in energy than visible, and this is what can cause a sunburn and skin cancer because the light has more energy than the ionization energy of DNA. Ionizing DNA can lead to cancer, although the body is amazing. So ionized DNA is conductive, and the electron hole travels to certain sites on the DNA, and that electron hole can be filled by a protein, but if you ionize DNA too much, eventually it can lead to problems. As we move to higher energy, we have X-rays that are good for imaging. So X-rays are absorbed by large atomic nuclei atoms like calcium. Well, they are mostly transparent for carbon, oxygen, and nitrogen and hydrogen. So you can do imaging where bones are, so you can see where the bones are with an X-ray. If we go to gamma rays, the energy gets even larger, and these are produced generally in nuclear reactions, and these are extremely high energy. If we go back to lower energies than visible light, we go past red and get to infrared. Infrared, you can feel to be warm, but is too low of energy for your eye to see. But if you're putting your hands near a fire, for example, and you feel a lot of warmth coming off of the fire, what you feel is the infrared radiation hitting your hands. If we go to lower energy, we have microwave radiation. So in microwaves, you use to heat up your cup of coffee. What happens? Well, the electric field generated by the microwave oscillates such that the water, which has a strong dipole, so it has a positive end and a negative end, and so as the electric field oscillates, the water molecules spin to align with it. And then as the water molecules spin back and forth, as the electric field oscillates, they pick up a bunch of energy and get quite hot. Notice that when they're in ice, they're locked in a lattice, they can't spin, so it's much harder to heat up ice than it is a liquid water. As we go to lower energies, we then have radio waves that are used for communication, as we sort of discussed with our discussion of antennas. So next we want to look at another way to create electromagnetic radiation. Before we talked about putting an AC voltage into an antenna, and that induced electromagnetic wave. Well, a simpler way to make electromagnetic radiation is to heat something up. Anything with a temperature is constantly emitting electromagnetic radiation, and this is called blackbody radiation. The best example of blackbody radiation is the sun. The sun is very hot, and the temperature of the sun, where it becomes transparent, produces visible light. So the sun emits visible light because its temperature there corresponds to the visible light range. If we take an old inefficient light bulb, so an incandescent light bulb, it also gets very hot, and so the tip of its blackbody spectrum is in the visible range, so we see it as a visible light. However, a lot of the electromagnetic radiation it emits is in the infrared range. This is why these old school incandescent light bulbs are obsolete. They produce way more infrared light than visible, so you waste a whole lot of energy when you use them. So everything emits blackbody radiation, even us. That's why if you have a good infrared camera, you can identify people because their body temperature is higher than their surroundings. Maybe you've seen a Predator movie. They're still making them, it seems. And so the Predator can see in infrared, so it can see what body temperature, so where you are or where you are not. Supposedly, when they shot the first movie, they really wanted to do it for real and shoot infrared video, but apparently it didn't work very well. So they made the actors stand right in front of a hot fire, so they got really hot, and then made them do the scenes. I've heard it sort of worked, but eventually they gave up and just did it with special effects. I think the big problem was that the jungle they were shooting in was just too hot. They didn't have enough of a temperature differential. Anyhow, everything emits EM radiation. The Earth emits microwave radiation based on its temperature, and that's part of the concept behind climate change, right? So climate change gases, so greenhouse gases, block infrared light emitted by the Earth, and it prevents that infrared electromagnetic radiation from escaping to space, so it causes the Earth's temperature to slightly heat up. If we look at the actual electromagnetic radiation produced by the sun, we see this red line here, which looks pretty close to the black body radiation curve. Notice that it spans ultraviolet, visible, and infrared light. Most of it is in visible and IR, but a decent bit of it is in ultraviolet. Notice when we look at what makes it through the Earth's atmosphere, a lot of the ultraviolet is blocked with only a bit going through. That's due to the ozone layer. Also notice that there are a number of water windows in the infrared region where usually water molecules absorbs a good bit of infrared radiation. So it isn't just ultraviolet that is blocked, other wavelengths are blocked as well. So for ultraviolet light, there are three types of ultraviolet light that correspond to different wavelengths. So UVC is the highest energy, and it is 100 to 280 nanometers, and basically very little is produced by the sun, and none of it makes it through the atmosphere. It's completely blocked by ozone. So ozone is a O3 molecule that pretty strongly absorbs ultraviolet radiation, and it's formed in the stratosphere, and this is what blocks our our ultraviolet light. So UVB is the next highest energy, and it's sort of the problem child that tends to cause sunburn and skin cancer. It is high enough in energy to cause problems, while some of it makes it through the ozone layer. Last we have UVA, which is the lowest part of ultraviolet. While it may cause problems, especially with eyes, it isn't so much a skin cancer problem. Remember, the cornea of your eyes, especially with eyes, it isn't so much a skin cancer problem. So remember, the cornea is especially prone to UVA light, while your skin is sort of okay with a UVA. That's one reason why you might want to wear sunglasses if you're out in the sun, because it's especially rough on your eyes. I had a colleague in grad school who was from Argentina, and his family was a bunch of sheep herders down near the southern tip of South America. It turns out that that is near the ozone hole, so there was a lot of UV light that was really bad down there. In any case, they had problems where their sheep were going blind because there was so much ultraviolet light that it would fry their corneas. So they bought a whole bunch of sunglasses for their sheep because otherwise they couldn't herd them, they'd all go blind. So for visible light, the visible light range is 400 nanometers to 750 nanometers because that is the range that the human eye can detect colors. So 400 nanometers, that is due to the cornea. So UV light is absorbed by the cornea, so we can't see shorter wavelengths than 400 nanometers. In fact, in some cases, people had really bad cataracts and they had their corneas shaved off. And those people can actually see into the UV. Claude Monet, the famous painter, in fact had this procedure late in his life, and some art historians say that you can tell the difference when he had this procedure. He could start to see in the UV, and his paintings became slightly different. This was also well after he was considered a master, so it probably didn't really help him too much. For longer wavelengths, the human eye has cones that are detectors that absorb at 3 different wavelengths of light. So there are 3 different kinds of cones, and each of them absorb a particular wavelength of light. So the longest wavelength that corresponds to red, there's a middle one that corresponds to green, and a short wavelength that corresponds to blue. So the human eye can detect lower wavelengths than 750 nanometers, but it can't identify color. Only the rods are stimulated, so it just kind of sees a white light. So the human eye detects color with 3 types of cones, so red, blue, and green, and then your brain basically disentangles this to identify a color. One interesting thing about this is that the wavelength that the green cones absorbs varies from one person to another. So if you ever wondered if you saw the same color as other people, the answer is probably no. Your eye detects different amounts of green depending on your genetics. So a bit of stoner science for you there. Notice, for evolutionary reasons, it is best for us to be able to see really well in the green region because we're trying to find predators and prey that are hidden in plant life, so having a better eyesight in the green range makes a lot of sense. So one extreme example of this is when someone's green cones and red cones line up with each other, so you effectively only have red and blue cones. This is pretty common, so about 5% of men and maybe 0.5% of women have this, and this makes them colorblind. So what kind of colorblindness is this? Okay, so next we want to know why the sky is blue. Well, there's no source of light when you look at the blue sky, so it must be coming from the sun somehow. But why is it blue? This is because the light bounces off of, or it scatters off of, particles and molecules in the sky, and the shorter wavelength light, like blue, scatters more easily than your longer wavelength light, like red. So when you look somewhere in the sky, a little bit of that blue light gets scattered and bounces off of the sky and into your eye. Notice that if you're looking at a sky with no atmosphere, then there would be nothing for the light to bounce off of, so then your sky would just look black. Alright, so why then is the sky red during a sunset or a sunrise? Well, it's really the same thing. When you are looking at the sun low in the sky, the light passes through a lot of atmosphere, and that scatters the blue light. So as the blue light scatters, the red light is left behind, so the sky looks red. Notice when you are looking at a sunset and enjoying the view, there is someone somewhere to your west looking up at the sky and thinking what a pretty color of blue the sky is, because that red light that you are seeing kept going through the atmosphere. Okay, so there's some questions here to do on your long kappa. They shouldn't give you too much trouble, but you do have a few questions to finish up. We're going to continue our unit on electromagnetic radiation on Thursday, so good luck with the questions, and take care of yourselves.